This conference will now be recorded.
So, good afternoon, everyone, and welcome to the latest SCLF webinar on gas risk assessment, which is going to be presented by Alex Staton. I'm just going to make him a presenter just now so that he can share his screen while I'm doing his introduction. Just a reminder to anyone that this session's been recorded, so if you don't want to appear in the recording, your image to appear in the recording, then make sure you put your camera off just now. And without further ado, I will introduce Alex. So Alex is a contaminated land specialist and hydrogeologist with 18 years experience in consulting. He's currently freelancing, so if anyone needs any work done with someone with that amount of experience, then please do get in touch. I'm sure he'll be able to give you his contact details. He's a SoBRA accredited risk assessor for permanent gases and controlled waters, and also a SiLC and SQP. His passion is in using the wide range of tools available to develop meaningful and defensible risk assessments, and he believes that good science is key. His scientific and methodological approach have often yielded more proportionate and cost-effective mitigation solutions, contributing to regular sign-off and enhanced client satisfaction. So without further ado, I will hand you over to Alec, and I think that's you. You are up and running. I think you just need to go back to the beginning of your...
Yeah, it looks a bit odd.
Yeah, I think it's something to do with what is shared. Have you got two screens?
Yeah, I have actually. That'll be why. Hang on. Oh, it's stuck. No, it's not. So how do I get rid of? I need just to reduce that. Right, got it. Need to close this. That just unplug it. That doesn't work. Thump it.
It did work a wee bit, half an hour ago, as usual.
Right. Okay. Is that right?
Okay, that's you. Right, take it away. Thank you very much.
Well, good afternoon, everybody. Thanks for tuning in. Gas is probably one of those subjects that does tend to generate quite a bit of interest. You know, it can be both sort of straightforward and confusing, and it is something that affects nearly every brownfield site that we're involved with. Well, oh, missed one out. Oh, where's that gone? I had some problem with my slides earlier. Okay, it's not there. I did have a picture actually of two incidents. The Losco one way back in the 80s when landfill gas migrated into a bungalow and there was an explosion. Thankfully, nobody was hurt, but the bungalow was totaled. More recently, there was the Gorebridge Incident.
Well, it's area wash. You went out for that contract for 3 years that we decided not to go for.
Yeah. But that was area wash planning.
Can whoever it is that's got their sound on put it off, please, because we can hear what you're talking about.
It sounds like Paul Nathaniel.
Yeah, it was. Yeah, it was.
Okay. So the Gorebridge Incident back in 2013, Scottish Government has been sort of investigating for the last few years various properties. The folk living there were complaining about various symptoms associated with carbon monoxide toxicity, and it was found in that instance that the carbon monoxide was getting into the properties from the mine workings below the site. And the upshot was that about it was 64 properties were subsequently demolished. The whole section of the housing scheme was knocked down, obviously at a very, very considerable cost. And last I heard, I think, as the Edinburgh City Council's pursuing the contractor for several £1 million. So I don't have a picture of that. I did have. Oh, what's happening to my slides? Oh, I don't know. Oh, excuse me. Right, try that again. That's it. There's been a great deal of guidance over the last few years. Well, say last few years. It's the last 30 or 40 years since the LOSTCO event, and new guidance continues to be produced. And I'm not going to go through this list of stuff, but folk will probably be aware of at least some of these. I suppose the sort of main sort of underpinning guidance at the minute is Sirius C665 from 2007. NHBC guidance picks up on much of that. So does the Ground Gas Handbook from 2009. But there's been some useful stuff sort of more recently, particularly some stuff by Claire, focusing on things like continuous gas monitoring and a more pragmatic approach to risk assessment for low-risk sites. And then perhaps most recently, there's that reference I put at the bottom there, risk and reliability in ground gas protection design 20 years on. That's a two-parter from CARD and others. And I'll say something about that in a wee while. Some of this is going to be dead easy. Conceptual site model. It's at the centre of every investigation and risk assessment. That's where we begin. I think it's probably fair to say that sometimes it isn't where we begin, particularly in relation to ground gas. We're very used to developing quite a, sometimes quite an involved conceptual site model for groundwater, for soil contamination and so on. But too often ground gas is kind of left as a sort of an add-on. And what we end up with is boreholes that are designed perhaps to monitor groundwater, or even boreholes that are designed principally for geotechnical reasons. We then just stick a standpipe, sometimes a very, very long standpipe, and just monitor them for ground gas, take the measurements, calculate a GSV, and that's it, and you've done it. Except that you haven't. And there are various problems with this, both in terms of missing potential sources and so underestimating risk, and sometimes it goes the other way, and we end up with risks where actually there aren't any. So these GSVs, they don't make any sense apart from the CSM. I think the intention, it's very easy just to turn to page whatever it is in Wilson and CARD, and just put the numbers in. We've got a flow rate, we've got a concentration, we calculate a GSV, and it's CS2 or whatever it is. That's wrong. If we're going to use the guidance, we should really start at page 1, and it talks about all of these issues. It talks about the CSM being iterative, and that we need to apply as much rigor to our investigations for ground gas as we do for anything else. Just a quick reminder of some of the sources. Landfills, perhaps the most obvious one, where we've got both, we usually got a high quantity of high organic containing material, and landfills, they go through a bit of a life cycle, but when they stabilize, you typically get methane at around 60% and CO2 at about 40. There's a bit of a range. It might be 40-60 or 60-40, and as you would expect, very often gas generation rates are very high. So much so, in fact, that a lot of local authorities, where they have got, admittedly, usually historical landfills, they're harvesting the methane and using it to heat the council office or drive the scoffy wagon or something like that. Mentioned Gorebridge, where the issue was mine gas. It wasn't methane in that particular instance, but you get both methane and carbon dioxide as well as carbon monoxide and hydrogen sulfide. The miners used to refer to the methane as fire damp and the carbon dioxide as black damp or choke damp. Both can be present at high concentrations. Perhaps less of an issue for flooded workings and for non-flooded workings, but certainly mine gas was implicated in the Gorebridge incident. It's sometimes possible to distinguish, sort of chemically between different sources of gas. I mentioned the typical concentration ratio in landfill gas. There are also a range of trace gases that would distinguish landfill gas from, say, mine gas. And it's sometimes when we're trying to, if we're struggling to get our CSM together, if we don't really understand where the gas is coming from, these kinds of analysis can sometimes be useful. And it can also be useful to take a bulk gas sample, a Tedler bag sample, maybe at least, if it's a relatively risky site, to take one just to sort of check against what you're getting in your monitoring instrument. So with landfill gas, with mine gas, peat, sometimes it can produce really very high concentrations of methane, maybe up to sort of 90%. But it tends to occur in pockets where it accumulates, and the rate of production tends to be pretty slow. You can get a rapid egress of methane from these pockets. You can get a sort of fairly rapid egress when you put the borehole in. It's going to take a wee while just to stabilize, but that isn't the rate at which the gas is being produced. And then there's sort of typical made ground, which I suppose is what we're dealing with most of the time. Made ground that's just made up of all the sort of usual stuff. Organic soils, rubbish, demolition rubble, ash, all that kind of thing. And most times we're getting fairly low concentrations, normally in the single figures, sort of maybe CO2 up at around maybe sort of 5–10%, methane, 0, or maybe up to 3 or 4 or 5%. And again, flow rates are very, very low. But I think this is an area where we sometimes do go amiss, is because we don't understand what's going on in the boreholes. We haven't given it sufficient thought. We perhaps haven't installed them especially well, and we're getting, we've done our sort of GSV, and we're getting numbers that are maybe suggesting CS3. And if you are getting that, then really you need to be taking that step back, thinking, is there something odd going on, or is there a source that I've missed? And there's a reference in that list that I gave earlier, Claire reference, and that deals specifically with made ground, with sort of low organic content made ground, and made ground that's relatively thin in terms of its thickness. And it's actually suggesting a pragmatic point, because it's such a low risk scenario. It's usually enough just to think about how thick the made ground is, what the organic content is, and it's going to be CS1, CS2, and there are screening thresholds provided for that. It's a useful way to go. Of course, we're not saying that you don't have any SI, because you need to know how much made ground there is. You need to know its organic content, but it's questionable whether you need to go much beyond that. Whether regulators always buy into that, that's maybe a separate issue. But I think certainly you can use the information in that bulletin as a part of a lines of evidence approach. There are a few other less significant sources. Things like petroleum hydrocarbons. If you've got petroleum hydrocarbon contamination in the groundwater, it's going to degrade, produce CO2 or methane. Sewage is an obvious one. Carbonate rocks, chalk, can produce carbon dioxide. Degassing of mineralized groundwater. CO2 is pretty soluble in water. Methane is also soluble, but less so. But the CO2 can naturally be there, and in the right conditions, it can degas. But the sources, that's just a wee diagram, a pinch from somewhere, I can't remember where. Looks vaguely familiar. It might be the NHBC guidance, actually. I meant to put the source, but it's just highlighting that the fact that there are these different sources, and it's also showing us the need to target them specifically. It's just not helpful if you've got quite a long screen, in a long well screen, and you just don't know where the gas is coming from. And that itself can give you all sorts of problems, as I'll just come on to in a minute. So migration mechanisms, essentially there are three. Advection, which is pressure-driven flow. It's flow under a pressure gradient from high pressure to low pressure, and that's often most significant in high permeability pathways. You're talking about gravels, sands, that kind of thing, but not silt and clay. And it's driven by Darcy's law. And anyone that's done any groundwater modelling will be familiar with that. So what that's saying there is that the flux Q is equal to the pressure difference over the pathway divided by the pathway length times a constant. And then there's diffusion, which is concentration-driven flow, which starts going from high concentration to low concentration. It has nothing at all to do with pressure. It's just a molecular diffusion, such as you might have seen at school when you're given the experiment. They give you there's a big length of tube, and they break a bit of bromine, an ampule of bromine at one end, and see how long it takes to get to the other. And that's molecular diffusion. For those of us who are more scatological bent, there are other obvious examples that you could give. So that's advection, diffusion. It's diffusions described by Fick's law, where the flux is just almost like the same as that equation for Darcy's law, except it's concentration over path length times the concentration, constant being a diffusion coefficient. And I've got a worked example at the end. And then the other one, and this appears to have been an instant a thing at Ware-McCry at Gorebridge. It's expansion of gas due to a fall in barometric pressure. That's described by Boyle's law. And so if you've got a volume of gas, at volume 1, and a pressure P1, then if the pressure drops or the pressure increases, then the product of the before and the product after, as shown in that equation, remains the same. So if the pressure drops, then for a given volume of gas, then the volume is going to increase. And the other one I mentioned there, degassing of groundwater. The gases are soluble. Carbon dioxide, quite, relatively considerably so. I had a note of it there. I think it's about 1,500 milligrams per litre. But if the pressure, it depends on pressure and temperature. Temperature in groundwater tends to stay fairly constant, but pressure could go up and down. Atmospheric pressure can go up and down, and at 980 millibars, for example, carbon dioxide is about 15% less soluble than at 1200 millibars. But there was a couple of instances where that was a real thing. There was a job I was involved in Dundee years and years ago, where we were getting some sort of sporadic concentrations of carbon dioxide in boreholes in a residential area. There is a huge old, almost dead landfill nearby, but there was no obvious pathway, and yet we were still getting these. So it was just literally a few percent, but it was enough that that SEPA was maybe a little bit concerned. So we kind of looked into it. We did a bit of geochemical analysis and presented an argument that they were changing from like nothing to a few percent over quite a short time, and it kind of led us to think that maybe pressure here was an issue, and the groundwater was oversaturated, and we felt that probably that's what was going on. Another odd one, sometimes it's good to sort of share the odd experiences we've had. Landfill out in East Renfrewshire, where we were getting sporadically slightly elevated concentrations of methane. And again, there was absolutely no reason why this should be. It was an inert landfill. You do get methane in inert landfills, but this one didn't make any sense. So we blasted it out, and lo and behold, we found a decaying mouse at the bottom of the borehole. And that was probably what was producing the methane. And once we'd done that, once we cleaned it, then it wasn't a problem anymore. So site investigation, I showed you that picture a few slides back. I've tried to emphasize that the SI needs to be targeted, needs to be designed with the CSM in your mind. So you might use targeted, non-targeted wells to give you a good lateral and vertical distribution. And I mentioned about targeting well screens to the source. So there are various reasons for that. You know, sometimes, you know, it's in the past, it's been a long well screen has been produced, and it's given you problems. It's not representative. You can get buildup of pressure in the headspace that doesn't really reflect what's going on the ground. It doesn't help you to identify source pathways pretty well, very easily. You can get issues with stratification. Carbon dioxide is heavier than methane. CO2 is heavier than air. Methane is lighter than air. So if you've got a long well screen, you could easily get methane accumulating at the top. And when you're just pumping with a GA2000 or whatever, you've not a hope of sort of equilibrating the borehole. And the other thing is just to carry out sense checks in the field. I think when we send folk out to do sampling, to do analysis, I think it's important for the project manager, whoever, or the technical lead, you know, to explain to the person why this has been done. And this is good for at least a couple of reasons. One of them is that it helps the graduate or the technician, whoever, you know, to engage better, to understand why we're just doing a thing. But the other thing, it helps them to sort of step back and think, well, that's a bit odd. You know, is that really right? Should I remeasure it? Should I do this? You know, perhaps phone the project manager, find out. And I think that can often save a lot of difficulty. Mentioned there, targeted well screens, you know, usually less than 2 or 3 meters, certainly not an awful lot more than that. So there are other things that we can do. Record everything, of course. Ask, do the measurements make sense? Is it worth repeating measurements? What about recording the buildup of gas in the borehole? You know, if we just get an initial whoosh and then it disappears, you know, what's going on there? Well, perhaps we could leave the bung off for a bit and, you know, let it purge effectively, and then go back and put the bung on and then record the increase in, you know, the rate of change over a period. Well, inertial data assessment, you know, some of these things come out of what I've said already. Know where the data comes from, understand where it's coming from. Don't just simply get, you know, you might have a big site and you just lump together all the boreholes. You say, well, that's the worst one for that, and that's the worst flow rate, so we'll multiply them and leave it at that. No, really what you should be doing is thinking about the geology, thinking about cross sections, thinking about where the boreholes target, are some of them flooded, and so on. Check for inconsistencies. We've talked about odd values. Check it's not a typo. Go back to field notes, speak to the technician, and set aside and think about it, but don't simply discard it. And equally, we don't want to assume that it's representative of the data set as a whole. If we've got just one borehole with an apparently highish concentration or a high flow rate, and it doesn't kind of sit with the rest, it may or may not be, because, you know, representative of the same volume of data. You know, you've got a huge big volume of made ground or of a source, and you've got maybe half a dozen boreholes. You know, it's quite conceivable statistically that you might get one with, say, 10% methane and another with nothing. Is that difference because the ground's different, or is it just, you know, ground substantially different, or is it just a sort of random effect? You need, it's getting back to knowing what it is that you're actually measuring. Zoning, can be okay, but only if the CSM supports it. Well, folk will have seen this, no doubt. It's from Syria C665. It's well, actually, it's this particular iteration's lifted out of NHBC, and that's what we usually do for for risk assessment. All of the work that sometimes gets missed is at the SI stage, at the CSM sort of stage, and it's only right at the end that you come to this table, to having calculated your GSVs. And note that there are a few notes in that. The column on the right ties in with what I was saying earlier. It's quite useful. So if you're getting CS3 and you've only got a meter of made ground, of sort of demolition rubble type made ground, and you're getting CS3, well, look to CS3. It says old landfill, inert waste, mine working, flooding. So it's so you're at the landfill sort of level. Okay, the low risk landfill, but what's more typical of made ground? Well, it's low risk to very low risk. It's not going to be moderate to high risk, or at least it's unlikely. It may be that. It may just be exactly that. But you need to just be giving it a wee bit of thought rather than just simply. And there's a good reason for that. What we write in reports is usually for the benefit of a regulator and a developer or a client. And if we've got a housing developer and we're saying, because we've got a couple of odd results that we haven't really thought about, that on that basis it's CS3 because it's just easier that way. Sometimes as consultants we can just put that in a report and then we send it out the door and that's that, and we don't give it any more thought. Meanwhile, the developer is seeing megabucks. I have it in my head that CS2 protection might be maybe around 100, might be about £1,000 for a plot. CS3 typically is 4 or 5 times that. So for a 500 home development, you're talking of well over £1 million. That's a lot of money, even on a large development. So when we're saying that something's CS3 or whatever it is, then we need to be really quite sure that that's what it is. Have a good idea that that's what it is. Don't just do it because it's easy. And there are consultants that, frankly, they are a wee bit like that. They just, it's the old sort of mentality of, I'll just put a meter of clay on it and classify it all as CS3. That's our job done. We've got our fee. Client might not be very happy about it, but but there it is. So understand the implication of what it is that you're recommending. So I mentioned, we just looked at the modified Wilson card. I'm not going to talk about this in any detail because it's really relatively hot off the press. It's that paper that I mentioned, Card et al. From 2019. The thing about the older version was that it's kind of more pragmatic than sort of science-based. There's not an awful lot of discussion on where these GSVs came from. But with this, what they've done is they've done some sort of backward reverse modeling, and there's a lot more science in this than there was in before. But there's a big literature search behind it as well. They looked at dozens and dozens of sites where gassing is there to try and understand what the actual risk is. So they kind of grounded it in reality. But they've also done this sort of reverse modeling, and included quite a few things that weren't included before. So things like, where have we gone? I've lost my place. Oh, here we are. Yeah, so they've got separate limiting values for methane and carbon dioxide. So gas regime A, which is essentially CS1, no special protections. That they've got values for methane of less than 2 litres per hour and less than 12 litres per hour for CO2. I mean, obviously that's orders of magnitude higher, 2 to 3 orders of magnitude higher than the values in the old table. So CS1, it was 0.07 litres per hour, Here we've got up to 12 litres per hour for CO2, the difference reflecting, I guess, their different hazardous properties, but also the way that they behave in the subsurface. And the other thing there is that they've got, a range, and it depends on the vertical ground permeability. Yeah, so it's lower, as you would expect, for lower vertical permeability, higher. The threshold is higher for lower permeability and lower for higher permeability. Ground permeability is a difficult one, particularly vertical permeability in saturated or even unsaturated sediments. Any form of permeability is difficult to measure. And I guess you're probably going to be relying on sort of literature, sort of base values. But you take the literature values. You need to understand what the geology is, of course. But as with all of these things, you want to do some sensitivity analysis just to check that that your conclusions are within a sort of a reasonable range. If it's more marginal, if it's closer to another one of the other gas regimes, then perhaps you need to either get more information or be a bit more conservative. Again, some useful notes attached to the table. At very high gassing, under very high gassing situations, essentially there aren't any limits, and you're looking at DQRA. And I'll say a wee bit about that in just a minute. Don't worry, I'm not going to say an awful lot, and I'm not that kind of far away. This is fairly recent. I'm not sure how much it's being used. For now, we are where we are. We're stuck with the British standard, which incorporates the modified Wilson-Card approach. So we use that. But again, I would imagine that this kind of information at this stage, it can still be useful and included as just to sort of help set things in context, I suppose, and just to apply a wee bit more science to what it is that we're doing. The key thing about this is that unlike the previous table, it's based on continuous monitoring. So I should probably say something about that. I don't know why the colours changed. But this is what we're talking about. Again, focus sort of thinking this is like a new thing, but it isn't. It's been around for at least 10 years. Claire produced a technical bulletin on continuous gas monitoring, and folk will probably heard about Ground Gas Solutions. They've been the guys that have kind of done a lot of the work on this. The images there are from Iron Science, which is they're the producer. But what you've got, the manufacturer. So you've got this thing that sits in the borehole. The tube sits down a standard 50 mil well. But you need a bit more headspace than you sometimes give in order to accommodate, the thing at the top. And what you get is these continuous monitoring traces. This one here is for methane in the dark color, and pressure in the red. And you see the very obvious relationship between the two. So that as pressure falls, the concentration of methane increases. Let's go back to that previous slide. So I've got my slides mixed up slightly. You can install these things. You can leave them. Make sure you've got secure headworks. The feeling in the industry seems to be that these are going to become more and more the way to go, and the information that you can get is sort of infinitely better than anything that you could get from a sort of standard sort of orifice type monitoring device. They're expensive to buy. They're about £7,500 each, but they can be hired fairly widely. And as I said, you can read off various parameters from a time series curve to understand how gas varies over time, much better than spot measurements. There was one site, again, another lesson, a site I was involved with long ago, and they'd done, I think, 4 or 6 spot measurements, and in the boreholes they'd found nothing. And then the site lay sort of fallow for a long time, wasn't much doing. Went back and did some more monitoring, and lo and behold, they did 4 measurements and found methane at relatively high concentrations. And eventually we installed some clams, and what had happened was that the methane would sort of go from 0 up to maybe 40–50%. If you were unlucky, you've got the you just got the trough. You recorded 0, but it went up, and you got so it was very, very variable. It was probably driven by barometric pumping in a well, which is something that you get in low permeability sediments. But it doesn't help that in this case, very long screen lengths, I mean really long screen lengths, had been installed that went through clay and into some organic silt, and then into some fluvial glacial sand and gravel. So I'm going to say a wee bit about DQRA. That type of measurement from the gas clams is very suitable for preparing a DQRA, although in reality, actually, the number of DQRAs you're going to be doing is probably very few. The idea is to calculate the ingress of gas into a property under the specific site conditions, so you need quite a lot of information. But crucially, the DQRA shouldn't replace robust assessment at earlier stages. And I think that's the thing. If you've got a bit of a ropey assessment, and then you've got, you think it's too conservative, but someone will just do a DQRA. That's probably not the way to do it. The way to do it is to go back and do the earlier stage of the assessment more thoroughly. Just go back to boreholes, go back to a cross section, look at how the groundwater is varying, look at how the ground gas is varying, look at barometric pressure and all of that kind of thing. But in any event, DQRA might be needed less if the new card approach is accepted by regulators. So I'm just going to finish up by a bit of maths sums for the Gorebridge incident. And I think I mentioned that the mechanism there, well, it's principally accumulation of gas around stone columns. And the gas gets there by diffusion through the clay. So the clay, the geology is about, the till's not that thick. It's around 5 meters or so. So let's just assume for now that the source is just at the base of the till. It's in the bedrock, in the core measures bedrock at the base of the till. Don't know what the concentration was, but just for these purposes, we'll assume 100%. Now we need the concentration gradient, we need the pathway length, and we need the diffusion coefficient. Now the diffusion coefficient, which is a constant of proportionality in Fick's law, depends on the gas and on the medium. CO2 diffuses easily in air, and much more easily in air than it does in soil or in dry soil. And CO2 diffuses much more easily in dry soil than it does in saturated soil. Now, there are various ways you can work out what the diffusion coefficient would be under the different conditions. You can use a value for air and calculate values for soil. And the upshot is that in saturated soil or in saturated clay, because that's what we're looking at, the diffusion coefficient is very, very low, 10⁻⁶ meters per day, if that means anything. And in dry soil, it's about 100 times higher. So we've got 5 meters of boulder clay. For the calculation, perhaps we'll assume that we're interested only in the till. We've gone with 100%. So the concentration gradient is 100% over the pathway length, which is 5, which gives us 0.2. And lastly, we need the footprint of the living space in which the gas accumulates. So the room I'm sitting in just now is about 4 meters by 4. On something more site specific, you could be more specific. So we've got gas diffusing at a flux rate determined by Fick's law into a room with a footprint of about 16 square meters. If you do the calculation, it comes up that the rate at which carbon dioxide is entering the floor, assuming there's nothing there, assuming it's just, there's no gas protection or anything like that, no concrete, it comes out about 0.003 liters of carbon dioxide per day. It's not much. It's very, very little. In fact, it's so little that you would probably never get a risk from that. If you say your room's, say, 4 by 4, say it's 2 meters high, gives you the volume, how long would it take to accumulate CO2 at a concentration of about 1.5% in that room? It's going to take forever. And actually, if you put the numbers in, it comes out about 75,000 days. So that suggests it's pretty unlikely that a critical CO2 concentration would accumulate under the circumstances I've described. All the more so if there's some if there's some level of protection. Even a concrete floor slab or a DPM would increase that time by some at least. But even a DPM would provide some protection. But if the soils are dry, then as I said there, that time decreases by a factor of 100. You wouldn't be too bothered, I wouldn't have thought, at the thought of CO2 accumulating over 775,000 days, but you might be a bit more concerned over 750 days. This actually supports something that's in the guidance in the new card paper, the effect that diffusion isn't likely to be important except where you've got dry soils, and very little, if any, form of structural barrier. Otherwise, it's not an issue. I think the lesson, though, is that diffusion is slow, but it can be an issue. So it's not something that we completely forget about. But what about stone columns? Well, I've said that it's perhaps relatively unlikely that diffusion by itself would be the problem. But if you've got stone columns, and those stone columns are displacing a significant amount of the clay, and if they're if they're shortening the pathway, it's already quite thin anyway, and it's quite conceivable that the carbon dioxide would diffuse into the space provided by the stone columns, and that if the pressure then drops, that reservoir of gas could then enter a property, via services or whatever, and that's exactly what they think might happen. Might have happened. You could carry out similar calculations for advection, but in general, as I said earlier, when you've got low permeability soils, advection isn't really a major issue. This does remind us, though, that just because you've got till, it doesn't necessarily follow that there's not going to be a risk. It's something to bear in mind. But the risk at Gorebridge is exacerbated by the fact that these preferential pathways have been created by the stone columns. And I suppose the lesson here is that while calculation can be useful, it can't account for every possibility. We might think we've got the best CSM that you can imagine. We know the geology and all of that, and we know how thick it is. We know how the groundwater is. We know where the gas is coming from. But if that CSM doesn't incorporate these preferential pathways, which really sometimes could knock everything else on the head, then it's really not worth much. You might say, well, they've got 5 meters of clay, it'll be fine. Gas doesn't pass through 5 meters of clay. Well, it might by diffusion, if not by advection. But then it's not just that. You've got these stone columns that have shortened the pathway length and have provided scope for a reservoir. And in the case of Gorebridge, it was all just too late. It was a very costly error. And well, it's important to be learning from incidents in the past. In that incident, harm had occurred, and it just wasn't feasible to do anything about it other than to pull the properties down. Well, just to wind up, what's the upshot? Spent too long on this, apologise. Thorough understanding of the CSM is essential. We've talked about that. For ground investigation, a thorough understanding of the CSM is essential for any risk assessment, and I think that's really the take-home message. Good investigation, but don't stop thinking about the CSM when you start calculating GSVs. There are various tools to assess, many more than I've been able to talk about. I think that very often risk assessments are probably are too conservative and need a reality check. I think the scope from moving away from a default CS2 or even CS3, where gas protection measures at that level aren't that warranted. But it needs to be science-based. We've discussed recent work by Card et al. That supports this conclusion. For now, we're stuck with modified Wilson and Card, but I think their work might be useful as a line of evidence in a more complex risk assessment. We passed briefly over DQRA, and lastly, we went back to the Gorebridge incident and did some very simplistic modelling. It's actually yielded a warning that while diffusion alone may not account for what happened, the reality is more complex. You do the calculations, but in that instance, there was more to it, and there was more to it that effectively set aside the result of the calculations, because preferential flow paths hadn't been considered adequately. It was a significant figure, a factor at Gorebridge, and this too easily overlooked. It raises the question we always need to be asking when we're doing our risk assessment, irrespective of what level we're doing it to. How well do we understand the CSM? Leave it at that.
That's great. Thank you very much, Alex. I'm just going to stop the recording now. So thank you very much again.